So, in the last lecture we started study of pure cubic fields and we started proving a theorem about finding ring of integers of this cubic field and its discriminant. So, let me recall what we did. So, pure cubic field we can assume without loss of generality to be of the form m1 m2 square. So, alpha 1 is cube root of m1 m2 squared. Alpha 2 is cube root of m1 squared, m2, m1 and m2 are square free positive integers, right. Then OK is z alpha 1 alpha 2, yeah, it is generated by these two if and only if m1 is not congruent to plus or minus m2 mod 9 and if m1 is indeed congruent to plus or minus m2 mod 9, then 1 by 3 1 plus m1 alpha 1 plus m2 alpha 2, this also belongs to OK. So, the index of this z alpha 1 alpha 2 in OK is 3 and this is the element that that represents the non-trivial class of OK mod this z alpha 1 alpha 2, right. So, this gives a complete answer. And in this particular case dk is minus 27 m1 square m2 square. In this case dk is minus 3 m1 squared m2 squared. So, so we were in the middle of proving this. So, what we had proved is, so we proved last time that delta square of 1 alpha 2 is minus 27 m1 square m2 square. This is also equal to a square times dk and a is 1 or 3, right. And we proved that a is 1 if 3 divides m1 or m2. So, the case that remains is, so the remaining case is 3 does not divide m1 m2. What happens in that case? So, in that case 3, there are two sub cases, this is p3 prime p3 double prime squared or 3 is totally ramified and it is p3 cubed. So, we have to consider these two cases. 3 is definitely ramified. So, you can't have 3 to be inert or 3 to be split or split into 2 primes because it is ramified. Right, okay. So, 3 is p3 prime p3 prime double prime squared and of course, here I am assuming that this is not equal to this if and only if x cubed minus m1 m2 square equal to 0 has a solution in Q3. Right. If it has a solution, it decomposes as a product of a linear factor times some degree 2 polynomial and we know that 3 is ramified. So, that degree 2 polynomial will further split as a product of same a square of something, right. So, in any case, so when does this have a solution? So, this is if and only if, this is almost like Hensel's lemma, but the slight generalization of Hensel's lemma that we proved earlier. So, this is if and only if x cubed minus m1 m2 squared congruent to 0 mod 9 has a solution. Okay, and when does this have a solution? So, what does Z mod 9 Z cross look like? So, this is I mean abstractly if you want, well concretely if you want, you can write it like this 5 7 and 8, but abstractly this is isomorphic to Z mod 6 Z right. The isomorphism is not unique, but it is isomorphic to this thing, and so the only way something is yeah, so the only cubes in here are plus and minus 1 right. So, this means that so you can check using this explicit thing or even using the fact that it is Z mod 6 Z, that this means M1 M2 squared is congruent to plus minus 1 mod 9 if and only if x cube minus M1 M2 squared congruent to 0 mod 9 has a solution. So, this has a solution if and only if this holds, right, which is same as saying that M1 is congruent to plus minus M2 mod 9, right, because the only square root of minus 1 in Z mod 9 Z cross is minus 1. Yeah, the only square root of 1 and minus 1 is yeah sorry yeah, I did not say that properly. So, M1 times M2 square congruent to plus minus 1 mod 9 is same as this. So, you have to do some checking there, but this can be checked easily, right. So, in particular if M1 is not congruent to plus minus M2 mod 9, then 3 is P3 cubed in K and dk is equal to delta squared 1 alpha 2, which is minus 27 M1 squared M2 squared right, and this is because as 3 is wildly ramified, and hence 3 to the power 3 divides the discriminant, right. We proved a result like this about different, and discriminant is simply norm of different. So, P3 cubed will divide the different of K over Q, and hence 3 cubed, which is norm of P3 cubed, will divide the discriminant of K over Q, right. So, that is we use that result here to conclude the case when M is not congruent to plus or minus M2 mod 9. We still need to show that 1 by 3 times 1 plus M1 alpha 1 plus M2 alpha 2 is in OK. So, let mu in Q3 be a root of x cube minus M1 M2 squared equal to 0, right. So, if we can write this as follows, okay. So, then alpha 1 minus mu alpha 1 squared plus mu alpha 1 plus mu squared equal to 0 in Q3. What we get then is, so what is alpha 1 square? We computed this earlier. So, this is M2 times alpha 1 plus mu alpha 1 plus mu squared. This is 0 in K sub P3 double prime, right. That is the, I mean this generates P3 double prime and this is related to P3 prime. So, we have this right. Yeah, but you see that alpha 1 is divisible by 3. So, you also have that mu 3 is yeah, I do not know what to write here. Mu is congruent to m1 mod 3. Okay. So, I want to analyze something like 1 plus m1 alpha 1 plus m2 alpha 2. And so, what do I do? Well, I know that modulo 3 mu square will be 1, right. So, okay, what do I know? I want to analyze something like this, but what do I know? I know that mu square plus mu alpha 1 plus m2, sorry, this should have been m2, because alpha 1 square is m2 alpha 2, yeah, sorry, that is the point of confusion. So, I know that mu square is 1 mod 3, I know that mu is m1 mod 3, so this is like this, and then m2 alpha 2, which is congruent to 0 because of this here mod 3, sorry, what did I, yeah, mod 3. Which is exactly what I wanted, because this means that this 1 plus m1 alpha 1 plus m2 alpha 2 is in OK. Right? This is what I wanted to show in the other case. All right. Okay, sorry. So, maybe one more, why is this true? So, mu congruent to m1 mod 3, this is precisely because you see mu is a root of this thing, right, and yeah. So, so mu minus right, mu minus alpha 1 is 0 in P3 cubed. So, if you take mod, the residue degree of P3 prime is 1, and so you get that mu is congruent to m1 mod 3, right. Okay. So, putting all these things together, we get that 1 by 3, 1 plus m1 alpha 1 plus m2 alpha 2 is in OK, which is what we wanted to prove. Okay, so we have now a complete answer of what the ring of integers of a purely cubic number field is, and what the discriminant is, right. But there is one more aspect to cubic field, and I am not going to give a general recipe for finding this, but what is the what's the rank of this as a Z module, right. So, you should pause the video at this point and try to find out the rank yourself, but I will tell you the answer now. So, R1 of k, which is the number of real embeddings of k, this is equal to 1, and R2 of k is also 1, right. And so, rank of OK cross, this is R1 plus R2 minus 1, which is 1. So, this has rank 1, which means that this situation is a bit like real quadratic fields, okay. And yeah, we will try to we will also see examples of finding units in real quadratic fields a little bit later, but let me do an example here which will illustrate both the theorem as well as how to find unit here. So, you take k to be cube root of 12, right. So, you can write 12 as 3 times 2 square. So, m1 is 3, m2 is 2, right. So, yeah. So, alpha 1 is cube root of 12 and alpha 2 is cube root of 3 square times 2, which is 18. So, you see that M1 is not congruent to plus or minus M2 mod 9. Hence, the ring of integers of this is Z alpha 1 alpha 2, right, and discriminant is minus 27 into 3 square times 2 square, which is minus 27 into 9 into 4, yeah, which is whatever it is. So, 27 into 4 is minus 108 times 9, which is 972 for whatever it is worth. All right. So, that gives you the discriminant, and now we want to find non-trivial unit, non-trivial meaning not a root of 1, non-trivial unit in OK, or even better like a generator of OK cross. So, what I am going to do next is I am going to ask you to compute norm of C0 plus C1 alpha 1 plus C2 alpha 2, and we will denote this by f of C0, C1, C2, and you can compute this norm and it turns out to be C0 cubed plus C1 cubed, sorry 12 times C1 cubed plus 18 times C2 cubed minus 18 C0 C1 C2. So, this thing is an exercise if you like. It is not a difficult exercise, but you have to do some computations. Okay. All right. So, what do we know after that? Okay. So, I am going to do something which is not necessarily very I mean yeah, I am not going to tell you the explanation of where these things really come from, but let us see, here is something I will do. So, we see that the discriminant is whatever it is. So, you see that if you take the ideal generated by 2 in here, then this is P2 cubed, we know this from our proof. The ideal generated by 3 is also P3 cubed. The ideal generated by 5, what is this? Well, I just look at x cubed minus 12 congruent to 0 mod 5. So, this is x cubed minus 2 congruent to 0 mod 5, right, and this thing has a okay, yeah, this thing has a root x congruent to 3 mod 5 is a unique root, right. And so, what we get is that 5 as an ideal is P5 prime and P5 double prime. Sorry, let me be a little bit neater here. So, this is P5 prime and P5 double prime. So, 5 is of course not ramified because it does not divide the discriminant, but it splits into 2 primes, and norm of one of those prime has residue degree 1 and the other of those primes has residue degree 2. So, this turns out to be 25 or 5 squared, right, because the residue degree is 2. Okay. So, now we are going to look at various combinations. So, you see that yeah, it turns out that f of 2 1 1, this is equal to 2, you can compute this. So, hence so I am just trying to find out what the ideal P2 etc. is. So, this is P2, f of 3 1 1, this turns out to be 3, and so we get 3 plus alpha 1 plus alpha 2 is P3. F of 5 to 2, this turns out to be 5, and hence 5 plus 2 alpha 1 plus 2 alpha 2. This is norm, right. So, this has to be the ideal whose norm is 5 rather than 5 squared, and then f of 0 minus 1 1, this is 6, hence alpha 1 minus alpha 2, this turns out to be P2 and times P3, right. Okay. So, having done all this, what is the use of all this? So, hence what we have proved is the following. So, you see that you compute the Minkowski bound. So, Minkowski bound for k is 7. So, you just have to sort of, or less than 7 in fact, right. And so, you just need to find factorization of all these primes which are less than 7. So, we will do other examples like this, and then this, when you revisit this calculation, this will become clearer, but let me just say, hence the class group of this is trivial, right, because all these ideals are principal ideals. Furthermore, what you get is the following. If you, so all these things are fine, but now you see there is a nice thing that comes out of all these calculations. The nice thing that comes out of all these calculations is that 2 plus alpha 1 plus alpha 2 times 3 plus alpha 1 plus alpha 2 is equal to the ideal generated by alpha 1 minus alpha 2, right. So, it is equal to this ideal. Oops. Right. What this means is that these two elements differ by a unit, and so you look at 2 plus alpha 1 plus alpha 2 times 3 plus alpha 1 plus alpha 2 divided by alpha 1 minus alpha 2, this belongs to OK cross. Now, of course, it can happen that this is a trivial unit, right. It can happen that this is a trivial unit, but you do the computation, and what turns out to be the case is that this is, so this is again an exercise. You have to use the relation between alpha 1 and alpha 2, alpha 1 square, alpha 2 square, alpha 1 times alpha 2 and so on, but this turns out to be 54, 55 plus 24 alpha 1 plus 21 alpha 2, and this turns out to be a unit, right. And here is a hard exercise, if you like to do it, that 55 plus 24 alpha 1 plus 21 alpha 2 generates OK cross modulo its torsion. So, this is what is called a fundamental unit. Okay. So, as I said, this is a somewhat difficult exercise to do, but it can be done. You can show that any unit is a power of this, an integer power of this. So, integer power could be negative as well. You can take this to the minus 1 and you will get another unit. So, and all these things are possible, you know, it is possible to do this computation. In some sense all this thing works because you have a principal ideal domain. If the class number were not 1, you would have to work much harder to get a unit, but because the class number is 1, you can write down all these relations and you get a unit. Alright. So, in today's class we finished the proof of theorem that gave the ring of integers in a purely cubic field, computed its discriminant, and we will look at some examples. In the next lecture, we will go back to real quadratic fields and see how to find a fundamental unit there, because the rank of the group of units in a real quadratic field is 1. And then we will look at biquadratic extensions. So, these are extensions of degree 4, Galois extensions of Q of degree 4 with Galois group Z mod 2 cross Z mod 2. Thank you.